Okay, now we're going to continue our discussion, our basic definitions in circuit analysis, by looking at the concept or the definition of the ideal circuit element, which is going to basically form the basis for everything we're going to look at in terms of the components we're going to use to build circuits and to analyze them. So what is the ideal circuit element at its highest level? Well, we can kind of think of it like so. I'm going to draw this block, and this block is going to represent our ideal element. And an ideal circuit element is going to have two connections or two terminals connected to it. I'm going to label these 1 and 2. And I'm going to define a voltage and current in terms of these two terminals. So I can, for example, define a current I flowing into terminal 1, which, if you think about it, if it flows into the terminal and comes back out, is also the same as the current that comes out of terminal 2. In addition, I can define a voltage between those two terminals in terms of polarity. So I can determine or define a voltage V, positive or negative. Now, I should point out that this polarity and these directions I've chosen are essentially arbitrary, but this gives me the basis for my definitions that we start with. So what are the properties of this ideal circuit element? First property is it has only two terminals. There are lots of electronic components that have more than two terminals, but as we're going to see later on, they can be modeled in terms of ideal circuit elements that have only two. In addition, and most importantly, the properties of the ideal circuit element can be described mathematically in terms of the voltage and current. So there is some way of describing how that element's going to behave in terms of voltage and or current. And third, we can think of the ideal circuit element as the atom of electrical circuit theory. In other words, we can't subdivide it. This is the most basic element that we can describe. All right? Now, in looking at the ideal circuit element, it turns out that the definition of power becomes critical to how we're going to describe how this thing works. So we recall. Remember we said that power is equal to the derivative of energy with respect to time, by definition. P is equal to dW dt, where power is in watts, energy is in joules, time is in seconds. We saw that definition before. And 1 watt must therefore be equal to 1 joule per second. Now, given this, I'm going to apply the chain rule from calculus, and I'm going to take this and rewrite this a bit differently. Let's take P and let's decompose it like so. P is equal to dW dt, which is equal to dW dq times dq dt. In other words, I am multiplying top and bottom by dq and writing now two derivatives. And hey, what is dW dq? We know what that is. That's equal to voltage. What is dq dt? As we saw last time, that's equal to current. And so this gives us something else that is necessary to understanding how ideal circuit elements work. And that's the idea that the power of an ideal circuit element must be equal to its voltage times its current. Now, if you look at this, you notice there's something here we haven't defined yet. I'm just saying P is equal to V times I, but as I said before, the way I defined the current going in and coming out and the voltage positive to negative, well, that was kind of arbitrary. How would this definition change if the current was flowing in the opposite direction, or if the voltage was negative to positive? As it turns out, in fact, we can kind of arbitrarily define that either way. So if you think about it, let's draw something here to kind of illustrate what the issue here is. So P is equal to V times I. The voltage can have a negative quantity, the current a positive quantity, or they can both be negative or they can both be positive. So in other words, if you think about it, power can either be positive or negative whenever you describe these terms. So power can be greater than 0. Power can be less than 0, depending upon those quantities. What does that mean? Well, when you have either positive or negative power in an ideal circuit element, it means that the element is either absorbing power or it's generating power. There's only one problem. Which corresponds to which? Is it this way? Does positive power mean it absorbs power, and negative power means the element generates power? Or is it the other way? Does positive power mean you're generating power, and negative power mean you're absorbing power? And if you think about it, this equation doesn't tell you that. Well, it turns out that we need some convention, some way that we all agree is the correct way to describe either absorbing power or generating power by an ideal element. And we give a name to that. We call that the passive sign convention, which settles this question for us. The passive sign convention, or PSC, as we will see many times. The PSC is effectively a universally accepted definition for resolving this question of what corresponds to what. So the passive sign convention gives us a universally accepted definition for resolving how we describe either power that's absorbed or power that's generated by an element. Now, I should emphasize, it is a convention, okay? So it's how we define it, how we choose to define it. If you think about it, we could mathematically create essentially a consistent system of circuit analysis choosing either one of these two conventions. But long ago, we all decided how we were going to do it. And that's what we're going to stick with here. So in order to understand the PSC, we just need to work a few definitions, and you'll see how it works. How do we use the PSC, the passive sign convention? Let's start with a circuit element. And just as we did before, I'm going to have terminals 1 and 2. I'm going to define the current as flowing in to the positive terminal and flowing out of the negative terminal as I define the voltage. So that's how we start the PSC. For a circuit element, let's define the directions and the polarities just as I've shown here. For a circuit element, we're going to define the direction of I so that it flows into the positive terminal and out of the negative terminal. And we know we can always do this. I can always flip it around to conform to this definition by simply changing the sign of the voltage and the current and either flipping the direction or flipping the polarity. Once we do that, let's calculate P is equal to V times I. Once we've done that, the passive sign convention says this. If P is greater than 0, if we have positive power, what that means is the element by the passive sign convention is absorbing power. And what it's going to do is that it absorbs power. It's absorbing energy. And either it's going to store that energy or it's going to dissipate that, perhaps as heat or as light or, depending on other types of elements we might look at, as some type of mechanical energy. So energy is either dissipated or stored. And this energy it's absorbing, this power that's being absorbed is coming from some other elements in the circuit. So it just isn't happening out of the thin air. There's something else connected that is supplying the energy, that is creating the power that this element is absorbing. So that's our first definition. What if P is less than 0 once we do this calculation? In that case, we have negative power. And in this case, what we say is the element is generating power and it is supplying it to other elements in the circuit. So this is what we're going to use this semester. Passive sign convention, positive or negative. Now, of course, there's a third choice too. Power could be equal to 0, in which case the element isn't absorbing or generating power. But if it's positive, the PSC says it's absorbing power. If it's negative, then it is generating power. And that is the universal convention we've all agreed upon in electrical engineering. Okay? Now, a consequence of how we do the PSC is this. By the passive sign convention, we define positive current as the flow of positive charge. So when you think about it, you've probably always thought about electricity as the flow of electrons. Well, okay. What's an electron? An electron is negative charge, so an electron moves through a conductor. What we're saying is for the passive sign convention, we're going to say that positive current is opposite. It's the opposite of negative charge, in the opposite direction. So that's positive current. In other words, it's opposite of the flow of electrons. And if you think about it, that makes sense. We defined current as a negative charge. Pardon me, I should say we define electrons as a negative charge. So if we're thinking of positive current, then that has to go the other way. Negative current would go in the same direction as electrons. Okay? Final thing we need to keep in mind is something you guys are very familiar with from your physics courses, which is conservation of energy. The conservation of energy is one of those universal principles in physics, and in fact it also applies in circuit analysis. If energy is conserved, then the rate of energy is also conserved. And therefore, according to the conservation of energy, the sum of all powers in a circuit must be equal to 0. In other words, the sum of all the powers that are generated plus the sum of all powers that are absorbed in a circuit. Keep in mind, these are negative, these are positive. If you add them together, they've got to be equal to 0. So this is one of the universal principles in circuit analysis. This will always be true. Power will always be conserved. The sum of all the powers and all the elements in any circuit must be equal to 0. And from now until you reach the end of this course, this will always be true, and we will continue to use this. It's always a way of checking your answer to make sure you work the problem correctly. Now, something else I want to add as well. Many people get hung up on the idea of adding the word generated or absorbed. So for example, let's say I've got an element, and that element has a power of 2 watts. You don't need to tell me that the element is absorbing 2 watts. You just have to say the power is 2 watts. Or if you have an element with a power of minus 6 watts, you don't need to say the element is generating 6 watts because it's got negative 6. Just say power is minus 6 watts. So when you look at the textbook has this big deal about saying the word positive versus negative in our text. Not necessary. The quantity and the sign tells me everything I need to know. So just think about that. I don't need any other kind of definition of absorbed or generated. No word added on. Just that number and the sign. And that describes exactly what the power of the element is. So let's just work a couple of quick examples to see how the passive sign convention works to finish this up. So let's say we have an element and we have 3 volts defined positive to negative between terminals 1 and 2. And I've got a 2 amp current flowing in to that terminal number 1. So in this case, look what I've done. I've defined the direction of current into the positive terminal. That's what the PSC requires. Now, of course, also implied is that 2 amps is flowing out through the negative terminal. Same thing. What is the power? Well, since I'm already conforming to the passive sign convention, P is equal to 3 times 2 is equal to 6 watts. So I've got a circuit that is absorbing 6 watts, positive power. Okay, that's an easy one. Let's draw a circuit element where it's not conforming to the PSC. Let's do this element. In this case, what if in this element, if you were given 5 volts positive to negative, but the direction of the current was 1 amp flowing out of the positive terminal? You cannot use P is equal to V times I. We're not following the passive sign convention. But fortunately, it's easy to make it follow the passive sign convention. How do we do that? By, for example, flipping the direction of the current and changing the sign on the quantity. If we do that, we are now following the passive sign convention. P is equal to 5 times negative 1 is equal to minus 5 watts. This element is generating power. It's got negative power. What if I had this example? Oh, incidentally, I could also do it this way. I split the current around, but it's also possible for me to do this. What if instead of switching the current, I switched the voltage? I flip the polarity, and now I've got minus 5 volts. Well, in this case, if 1 amp is flowing out here, that means 1 amp is flowing in. Now 1 amp is flowing into the positive terminal. And what do you know? Now it follows the PSC. In this case, P is equal to minus 5 times 1, which gives you exactly the same answer. It's still minus 5 watts. So I could have defined it either way and gotten exactly the same answer. Let's do one more example. Let's say in this case, I've got 3 volts, negative to positive between terminals 1 and 2. And minus 4 amps flowing into the negative terminal. Okay? How do we use the PSC for this? Well, if I've got minus 4 going into the negative terminal, that means I need to have minus 4 amps flowing out of the positive terminal. What goes in must come out. Okay? Let's make this conform to the PSC. So in this case, I'll flip the direction of the current around. I've now got the direction going in where it's 4 amps going into the positive end. And therefore, in this case, P is now equal to 3 times 4 is equal to 12 watts. And once again, I've got an element that's absorbing power. So as you can see, you can always flip around the voltage or the current in order to make this conform to the PSC. The direction of the current must enter the positive end. That's what you have to remember. And then you can write down P is equal to V times I. Now, one final concept we're going to need. That's the concept of the voltage rise or the voltage drop. This is something that when people first see it doesn't necessarily make a great deal of sense until you start actually analyzing circuits, and then everything will click. But I want to introduce it to you now. The voltage drop and the voltage rise in some ways are kind of arbitrary definitions because it turns out you can kind of use either definition depending upon the way you look at an element. So let's look at two different elements here. Call this A and this B. So in this case, I've got a voltage of 1 volt across this element from terminal 1 to terminal 2. And let's say I've got a current that we have defined flowing in to the positive terminal and out the negative terminal. So I'm just going to kind of follow this current around like I was basically going with the flow. I'm going to come into the positive and go out the negative end. And if I do that, I say that this going positive to negative through this element, I call that a voltage drop. So from terminal 1 to terminal 2, I say I have a voltage drop, positive to negative, of 1 volt, the way I've drawn this element. Let's look at element B over here. So in this case, let's assume I've got a voltage negative to positive, and the direction of the current is defined as entering the negative end. So once again, I'm kind of riding along that flow, and I move into the negative end and come out the positive end. In this case, I'm going from a negative to positive. And so in this case, I say this element has a voltage rise. Of 3 volts, negative to positive from terminals 1 to 2. Okay, as I said before though, this is kind of arbitrary. And what do I mean by that? Well, as we already know, it's very easy to flip these definitions around. Let's do this. Let's make that negative to positive minus 1 volt. Let's make this positive to negative of minus 3 volts. So I've simply flipped the polarities and changed the sign of the voltages. And if I do that, I can now flip this definition around. I can now say it has a voltage rise of minus 1 volt. Over here I can say now it's positive to negative, or it has a voltage drop of minus 3 volts. So it's really, in many ways, very arbitrary. What I call a voltage rise or a voltage drop is strictly a matter of how I define the voltages, polarity of the voltage and the direction of the current, and I can always flip around those definitions. And so later on, as we do circuit analysis, as you find yourself tracing paths through a circuit, you're going to be moving through a path where you're either going to see a voltage go positive to negative and call it a drop, or negative to positive and call it a rise. And later on, as you start doing analysis and writing those equations, these definitions will really become very much second nature. Okay, so this kind of wraps up all of our basic definitions. Next time we're going to go through and we'll look at our 5 basic circuit elements that we're going to be using in this class and start looking at how we defined those. And of course, all of these are going to be based on the concept of the ideal circuit element.